Hello dear students, welcome to the lecture 9 of Artificial Intelligence and Machine Learning. So let's start with today's first topic, which is evaluation.
Supervised evaluation.
In supervised evaluation, we know the data labels, therefore we can accurately evaluate our training model's performance. So we have training data like this, and we have testing data. And when we are training our model, we don't show the test data to our trainer. Therefore, the model has no idea about the testing data. And since we know the label of the testing data, we can evaluate the predicted class was whether correct or not. So here, training data, trainer classifier, and compose a model, then use that model to test the unshown data to the trainer and pretend like we don't know the labels. So when you provide test data to the model, you don't provide its labels to the model, of course, and you compare the output of the model with the labels that you know. Okay, it is displayed here. So we provide the data without label, and model classify them, and then we can calculate the accuracy of our model because we know the true labels of the testing data. Okay, compare predicted labels to actual labels. And okay, so the first model produces 1 and 1, the second model produces 1 and 0. Obviously the model 2 is better because it has 100 accuracy in this example. Model 2 is better if score 2 is better than score 1, of course. When would we want to do this type of comparison? When we want that, let's say we just need high accuracy on. Actually, we don't just compare single evaluation results because that particular data might be good for a certain model, but it might be worse for all of the other models. Okay, so this would be our concern with single type of comparison. Okay, here another example. So let's say we have two algorithms to generate a model. The first algorithm generates model 1 and the second algorithm generates model 2. And we have three different data sets to train and test. Okay, so in the first data set, the first model generates 85% accuracy, and the second algorithm generates 80% accuracy. On the second data set, the first model generates 75.5 accuracy, and the second algorithm generates 75 accuracy. And on the third data set, the model 1 generates 0 accuracy and the model 2 generates 100 accuracy. So you see, on three different data sets, the more generalized, or let's say the better performing overall algorithm is algorithm 2. Okay, so you should have different data sets to compare different algorithms accuracy performance. That is why we use Enfold cross validation, which we will see in this lecture.
Comparing scores, significance. Just comparing scores in one data set isn't enough. We don't just want to know which system is better on this particular data, we want to know if Model 1 is better than Model 2 in general. Put another way, we want to be confident that the difference is real and not just due to random chance.
Okay. So model 2 better if score 2 plus C bigger than score 1. This is the idea, second idea. Okay. This is
No. Key, we don't know the variance of the output.
okay.
Variance. Recall that variance or standard deviation helped us predict how likely certain events are. How do we know how variable a model's accuracy is?
We can't know. Therefore,
We need multiple accuracy scores. Ideas.
how can we have multiple accuracy scores to evaluate a model, an algorithm is better than another algorithm, another model? Okay, so let's see.
Repeated experimentation.
Okay, with repeated experimentation, we can have multiple accuracy scores.
Rather than just splitting once, split multiple times.
Okay, so here on this example, we split with just one time. Okay, we split it here and we use the first 5 data as training data and the last 2 data as testing data. However, on repeated experimentation, we can split it like this, you see. And at the first model generation, we use first 4 as training and last 2 as testing. At the second model generation, model training, we use the first one as training, second one as testing, third one as training, fourth one as testing, and the last 2 one as training. And on the another model training we use like this, and so on. So this is called as
Enfold cross-validation.
so we have training data
Training data.
with labels, or if we are doing supervised classification or clustering, doesn't matter.
Break into n equal size parts.
So we break that into n equal size parts.
Repeat for all parts, splits. Train on n1 parts, optimize on the other.
So with this way we obtain n different models and n different scores with just a single algorithm. Okay.
Enfold cross-validation. Better utilization of labeled data. More robust, don't just rely on one test development set to evaluate the approach or for optimizing parameters. Multiplies the computational overhead by n, have to train n models instead of just one.
So this is the negative side of Enfold cross-validation, because it uses more computation, more time, therefore.
10 is the most common choice of n.
So let's say you are writing an article or doing a homework or project like what I have given you. You have to use at least 10-fold cross-validation to evaluate your algorithms, your system accuracy performance. Okay. Okay.
Leave one out, cross-validation. Enfold cross-validation where n equals number of examples, aka jackknifing.
Okay, so first let's look for a better example of Enfold cross-validation. Okay. I will look for a article with good pictures. Okay, I think this is a good one. Yeah, let's read here as well so you will get the idea. It can be called as K-fold cross-validation as well.
K-fold cross-validation. Evaluating a machine learning model can be quite tricky. Usually, we split the data set into training and testing sets and use the training set to train the model and testing set to test the model. We then evaluate the model performance based on an error metric to determine the accuracy of the model. This method, however, is not very reliable as the accuracy obtained for one test set can be very different to the accuracy obtained for a different test set. K-fold cross-validation (CV) provides a solution to this problem by dividing the data into folds and ensuring that each fold is used as a testing set at some point. This article will explain in simple terms what K-fold CV is and how to use the sklearn library to perform K-fold CV. What is K-fold cross-validation? K-fold CV is where a given data set is split into a k number of sections, folds where each fold is used as a testing set at some point. Let's take the scenario of 5-fold cross-validation, k equals 5. Here, the data set is split into 5 folds. In the first iteration, the first fold is used to test the model and the rest are used to train the model. In the second iteration, second fold is used as the testing set while the rest serve as the training set. This process is repeated until each fold of the 5 folds have been used as the testing set.
Okay, there is a key issue here I will explain you. So it is shown like this. However, each one of these is actually a separate training. So you train a model on here and test it. Okay, so you use I will pick this one for testing and this for training. So model A is here. Let's say accuracy 97%. And here you start again from 0. So these 4 are used for training a model and this for testing. So here model B is here. Let's say accuracy is 75%. And same applies here. We generate another model here and another model here and another model here. So we get total 5 models. Okay, with 5 folds cross validation, we train 5 different models. We obtain 5 different accuracies. And we take the average of these obtained accuracies to determine the accuracy of our algorithm. Okay. So with this way, you can call. Let me write it. You can compare accuracy, therefore success of different algorithms to pick which ones work best on your problem. Okay, so this is the way it is. Why we use Enfold cross-validation is to compare success of different algorithms to determine how they are fitting for our problem, how they are good to solve, and how well they generalize for our problem. If we use single set, if we use single set to determine our algorithm accuracy, it may be that particular data set is either too good for that algorithm or too bad for that algorithm, and that wouldn't reflect the overall performance of that algorithm. So a data set can be very bad or very good for that particular algorithm. Therefore, we need to have more tests. We have to test our algorithm on multiple data sets to evaluate its overall performance. Okay, let's continue. So leave one out, cross validation. Okay, let's continue.
Can be very expensive if training is slow and or if there are a large number of examples. Useful in domains with limited training data, maximizes the data we can use for training.
So leave one out cross validation is we only leave the one data out from training and use the rest as training, as far as I remember. Let's see it. You see, it is proposed in 1982, probably. Okay, so this is, it can be also leave P out, cross validation.
Leave P out cross validation. Leave P out cross validation (LPOCV) involves using P observations as the validation set and the remaining observations as the training set. This is repeated on all ways to cut the original sample on a validation set of P observations and a training set, 12.
Actually, this is no different than Enfold cross validation. This time, we don't split the set by percentage, but we split it by number. It can be 10, it can be 20. So let's give an example to illustrate this better. Let's say we have a data set of 10,000 objects with labels. If we use tenfold cross validation, then our each fold is being 100 objects. Okay, so at each model training, 100 objects are being test set and 900 objects are being training set. If we use, let's say, 10 out cross validation, then at each model training, 10 objects are being test set and 9,900 objects are being training set. So on this example, on Enfold, we do 10 different model training. On this one, we do 100 different model training, and if we use leave one out cross validation, then only one object is being used for testing in each model training. Therefore, we do 1000 model training. So of course, if you do leave one out cross validation, you would get the best average score. I mean, your model your score would reflect its performance best. Okay. However, it would take 100 times more time than tenfold cross validation. Okay, it is so easy. Okay, so this is the illustration of leave one out cross validation. You see each time one is used as test and the others ones as used as training. From you, I want tenfold cross validation in the project because that is the most commonly used evaluation methodology.
Comparing systems, sample 1.
Okay, so in this example, there are two different algorithms and we do tenfold cross validation. So here you see their averages are same. Okay. However, which one do you think is better than the other one? Which one do you think and why? Okay. So let's think a moment about that. So in this model 1 and model 2, by the way, model 1 is being an algorithm and model 2 is being another algorithm because they are trained and tested on the same data set at each split. Okay, so we can compare them. Okay, which one do you think is better one? Okay. From just looking the mean and max, the difference between mean and max at model 2 is 10 and at model 1 it is 7, I mean 8. Therefore, since mean and maxes of model 1 is smaller than model 2, I would say model 1 is better. Okay, because it produces more stable results than model 2. Okay, so on this example, can we say model 2 is better than model 1? Yes, because its average is better. And on this example, can we say model 2 better than model 1? Yes, we can say because its average is better. Okay, so on here, what is the difference? You see they have both averages same. However, the difference is the I think variance of accuracies. It is also explained here.
Even though the averages are same, the variance is different.
You see there is standard deviation as well. So variance is also important. Therefore, you should pick lesser variance and lesser standard deviation having models if they do same performance. Okay. And when we compare these different examples, Model 2 is being better in terms of both standard deviation and accuracy averages. Okay. There is also other ways to determine which model is better than just simply comparing their standard deviation or averages. We can do,
Statistical tests.
sorry.
Setup. Assume some default hypothesis about the data that you'd like to disprove, called the null hypothesis. E.g., Model 1 and Model 2 are not statistically different in performance.
Okay, so this is being our null hypothesis and we want to disprove that. Okay, we say that they are not statistically different and we want to disprove that. If we disprove that they are same, then we can know which one is better than the other one.
Calculate a test statistic from the data, often assuming something about the data. Based on this statistic, with some probability we can reject the null hypothesis, that is, show that it does not hold. Determines whether two samples come from the same underlying distribution or not.
Okay.
T-test. Null hypothesis, Model 1 and Model 2 accuracies are no different, i.e. come from the same distribution. Assumptions. There are a number that often aren't completely true, but we're often not too far off. Result. Probability that the difference in accuracies is due to random chance. Low values are better. Calculating t-test. For our setup, we'll do what's called a pair t-test. The values can be thought of as pairs, where they were calculated under the same conditions. In our case, the same train test split gives more power than the unpaired t-test. We have more information. For almost all experiments, we'll do a two-tailed version of the t-test. Can calculate by hand or in code, but why reinvent the wheel? Use Excel or a statistical package.
Okay, so there are three different sources to understand students' t-test. So let's get some more idea.
The t-test is any statistical hypothesis test in which the test statistic follows a student's t-distribution under the null hypothesis. A t-test is the most commonly applied when the test statistic would follow a normal distribution if the value of a scaling term in the test statistic were known. When the scaling term is unknown and is replaced by an estimate based on the data, the test statistics, under certain conditions, follow a student's t-distribution. The t-test can be used, for example, to determine if the means of two sets of data are significantly different from each other.
Okay, there are some history and such if you want to learn. Okay. Okay, there is a paired Tts Calculator. So I think we can put our data here to calculate. Let's put our data to there. So this is our model 1 and model 2. It didn't work that way. Maybe this will work. Okay, let's split it to data. Here, okay, so this one and this one calculate. Okay, it says like this. This is the distribution. Test validation hypothesis is shown like this. Okay, so I think from here we can assume that they are statistically different when we use these tails. You see, our hypothesis is they are not equal. Significance level is 0.05. Outliers included, effect medium, effect size 0.5, standardized effect size, and digits 4. And from this, we know that our hypothesis is true. If we use this one, let's see. Yeah, it is also true. Okay, so this hypothesis is being rejected. If we do like this, okay, so this hypothesis is being accepted. Therefore, we say that they are not same. Okay, this is some statistical thing I also don't know very well. So if you want to check them statistically, you can do more research. Okay, there's another website.
Tts Calculator for two dependent means. Enter your paired treatment values into the text boxes below, either one score per line or as a comma-delimited list. Remember, because the t-test for two dependent means uses paired values, you need to have the same number of scores in both treatment conditions.
Okay, so let's test with this one. Treatment 1, treatment 2. P significance level as 0.05. I think this is the standard significance level, and we use two-tailed calculate. Okay, it calculates mean, standard deviation. Okay, and okay, so you see the result is significant, therefore they are different. Okay.
The output of this calculator is pretty straightforward. The values of T and P appear at the bottom of the page. If the text is blue, your result is significant. If it's red, it's not. The only thing that might catch you out is the way that we've rounded the data. the data you see in front of you, apart from the t and p values, has been rounded to two significant figures. However, we did not round when actually calculating the values of t and p. This means that if you try to calculate these values on the basis of the summary data provided here, you're likely going to end up with a slightly different and less accurate result.
Okay, so since our result is blue, that means the result is significant. The significant means here that they are significantly different. Therefore, we can say that the model 2 on our example is better because the model 2 generates better average, and since they are significantly different at the t-test, therefore we can say model 2 is better. Okay, there are some also extra statistical tests. Okay, let's read it. Okay, I think I have internet problem. I will pause. Okay, p-value.
The result of a statistical test is often a p-value. P-value, the probability that the null hypothesis holds. Specifically, if we re-ran this experiment multiple times, say on different data, what is the probability that we would reject the null hypothesis incorrectly, i.e. the probability we'd be wrong? Common values to consider: significant 0.05, 95% confident, 0.01, 99% confident, and 0.001, 99.9% confident. Comparing systems, sample 1. They are the same with p equals 1.
Okay, so in this example, they are same. Let's test this on the website as well to verify if it is true or not. Okay, and okay, here and here. Yes, true. The value of t is 0, the value of p is 1, the result is not significant. Okay. So in this example, they are same. The first algorithm and the second algorithm performance same. Okay. So in the second example, the first algorithm and second algorithm, it says they are the same with p 0.15. However, when we use p equal to 0.05, I think they are not being same. Oh, we didn't test this maybe. Let's test this as well. Okay, and okay, the last days I 77 and 75, and here let's test them. Yeah, it is true. This example, in this data set, the first algorithm and the second algorithm are statistically same. Their average is different. However, when you take into consideration their variance as well, they are statistically same. You see there is a difference of 11, 13 between min and max of model 2 and 18 between min and max of model 1. Even though the model 2 has a higher average, they are statistically same. Okay. However, in this example, they are not same because you see it has very high confidence. Therefore, in this example, model 2 is better. Since in this example, model 2 has higher accuracy, I mean higher average, we can say model 2 is more preferable. You should depend on the statistical test because it is universally accepted.
Statistical tests on test data.
Okay, all training data, test data, no peeking. You don't provide test data to training. Okay. This way, it may be better. Okay, before doing training, what else you can do? You can do this. I think I had explained this before, but let me explain. So let's say you have 1000 labeled data, and you have 5 different algorithms. Okay. And what we are going to do is Bootstrap Resampling. Let's read it, then I will explain.
Bootstrap Resampling. Training set T with n samples. Do m times. Sample n examples with replacement from the training set to create a new training set T. Train models on T. Calculate performance on test set. Calculate t-test or other statistical test on the collection of m results.
Okay, so what does this saying is, I think this example is not very good. I will look for a better one. Okay, let's read this one.
A gentle introduction to the Bootstrap method. The Bootstrap method is a resampling technique used to estimate statistics on a population by sampling a dataset with replacement. It can be used to estimate summary statistics such as the mean or standard deviation. It is used in applied machine learning to estimate the skill of machine learning models when making predictions on data not included in the training data. A desirable property of the results from estimating machine learning model skill is that the estimated skill can be presented with confidence intervals, a feature not readily available with other methods such as cross-validation. In this tutorial, you will discover the Bootstrap Resampling method for estimating the skill of machine learning models on unseen data. After completing this tutorial, you will know: the Bootstrap method involves iteratively resampling a dataset with replacement. That when using the Bootstrap you must choose the size of the sample and the number of repeats. The scikit-learn provides a function that you can use to resample a dataset for the Bootstrap method. A gentle introduction to the Bootstrap method by Jason Brownlee on May 25, 2018 in Statistics tweet share. Bootstrap method. The Bootstrap method is a statistical technique for estimating quantities about a population by averaging estimates from multiple small data samples. Importantly, samples are constructed by drawing observations from a large data sample one at a time and returning them to the data sample after they have been chosen. This allows a given observation to be included in a given small sample more than once. This approach to sampling is called sampling with replacement. The process for building one sample can be summarized as follows. Choose the size of the sample. While the size of the sample is less than the chosen size, randomly select an observation from the dataset, add it to the sample. The Bootstrap method can be used to estimate a quantity of a population. This is done by repeatedly taking small samples, calculating the statistic, and taking the average of the calculated statistics. We can summarize this procedure as follows.
I think this is confusing. Let's look for a better one. Okay, so this is our original sample with sample size n, b sets of bootstrap sample size of n, b sets of bootstrap sample size of n, b sets of bootstrap estimates it estimates 1, 2, 3 further inherence. Okay, let's read this one.
Problems with the process of estimating these unknown parameters are that we can never be certain that are in fact the true parameters from a particular population. How can we be sure that they are not biased? How can we know how far from the truth are our statistics? This is when Bootstrap and Jackknife were introduced. Bootstrap and Jackknife are statistical tools used to investigate bias and standard errors of estimators. Both are resampling, cross-validation techniques, meaning they are used to generate new samples from the original data of the representative population.
Okay, so what is Bootstrap?
Bootstrap is a method which was introduced by B. Efron in 1979. Bootstrap uses sampling with replacement in order to estimate to distribution for the desired target variable.
Okay, it's also not explaining well. Okay, so this is our original sample with sample size n, b sets of bootstrap sample size of n, b sets of bootstrap estimates 1, 2, 3 further inheritance. Okay, let's read this one. Problems with the process of estimating these unknown parameters are that we can never be certain that are in fact the true parameters from a particular population. How can we be sure that they are not biased? How can we know how far from the truth are our statistics? Okay, I'm looking for a good and clean example. Okay, I think what does this means is we create n times samples by separating data as test data and training data, randomly picking elements. Okay, yes, it is what it is. Repeat m times to get m samples, sample with replacement. Okay. Okay, so I think it is like this. Let's say we have data as A, B, C, D. So we will compose four samples. And the first sample A, B, C will be training, D will be test. At the second one, it will be A, B, D will be training, B will be C will be test. I am giving a small number of examples. However, maybe there are some online resampling. So basically, what does it is? It composes different samples. At each sample is randomly composed, and whatever you put in training data is not put into test data. It is like Enfold cross validation. However, this time it is not picking certain faults. It is random. Okay, this is the difference, and yeah, this is the difference between Bootstrap. I will look for something. Okay, someone has already asked it.
What is the difference between bootstrapping and cross-validation? I used to apply K-fold cross-validation for robust evaluation of my machine learning models. But I'm aware of the existence of the bootstrapping method for this purpose as well. However, I cannot see the main difference between them in terms of performance estimation. As far as I see, bootstrapping is also producing a certain number of random training plus testing subsets, albeit in a different way. So what is the advantage for using this method over CV? The only thing I could figure out that in case of bootstrapping one could artificially produce virtually arbitrary number of such subsets, while for CV the number of instances is a kind of limit for this. But this aspect seems to be a very little nuisance.
Okay, this is the question that comes to my mind exactly. So someone has explained it. Let's see it.
Both cross-validation and bootstrapping are resampling methods. Bootstrap resamples with replacement and usually produces new, surrogate data sets with the same number of cases as the original data set. Due to the drawing with replacement, a bootstrap data set may contain multiple instances of the same original cases, and may completely omit other original cases. Cross-validation resamples without replacement and thus produces surrogate data sets that are smaller than the original. These data sets are produced in a systematic way so that after a pre-specified number kk of surrogate data sets, each of the nn original cases has been left out exactly once. This is called k-fold cross-validation or leave x out cross-validation with x equals nk x equals nk, e.g. leave 1 out cross-validation omits one case for each surrogate set, i.e. k equals nk equals n. As the name cross-validation suggests, its primary purpose is measuring generalization performance of a model. On contrast, bootstrapping is primarily used to establish empirical distribution functions for a widespread range of statistics, widespread as in ranging from, say, the variation of the mean to the variation of models in bagged ensemble models. The leave one out analog of the bootstrap procedure is called jackknifing and is actually older than bootstrapping. The bootstrap analog to cross-validation estimates of generalization error is called out-of-bootstrap estimate because the test cases are those that were left out of the bootstrap resampled training set. That intuition is correct. In practice, there's often not much of a difference between iterated kk-fold cross-validation and out-of-bootstrap. With a similar total number of evaluated surrogate models, total error of the model prediction error measurement has been found to be similar, although OOB typically has more bias and less variance than the corresponding CV estimates. There are a number of attempts to reduce OOB bias, 0.632 bootstrap, 0.632 plus bootstrap, but whether they will actually improve the situation depends on the situation at hand.
Okay, so we learned that on practice, k-fold is a little bit better than bootstrap sampling, therefore you should use that. Okay, so I'm going to pass this. If you are more interested in that, you can look for it. So I will take a pause for a moment. Okay, part 2 of lecture 9, multiclass.
Multiclass classification. Same setup where we have a set of features for each example. Rather than just 2 labels, now have 3 or more.
Actually, on real-world data problems, you will usually have multi-class problems to solve, and in the previous lectures, the examples I have made were all multi-class. Okay.
Real-world multiclass classification.
Document classification, protein classification, handwriting recognition, face recognition, sentiment analysis. Most real-valued applications tend to be multi-class. Autonomous vehicles, emotion recognition.
Multiclass, current classifiers.
Okay, so what classifiers we have? We have perceptron classifier, for example, which can separate data into 2. And we have KNN.
To classify an example D, find K nearest neighbors of D. Choose as the label the majority label within the K nearest neighbors.
So KNN works without any algorithmic changes, and it can classify multiple labels. Okay. Decision tree.
Decision tree learning. Base cases. 1. If all data belong to the same class, pick that label 2. If all the data have the same feature values, pick majority label 3. If we're out of features to examine, pick majority label 4. If we don't have any data left, pick majority label of parent 5. If some other stopping criteria exists to avoid overfitting, pick majority label. Otherwise, calculate the score for each feature if we used it to split the data, pick the feature with the highest score, partition the data based on that data value and call recursively no algorithmic changes.
So decision tree and KNN works on multi-label class problem as well. Okay, let's continue. So perceptron learning.
Perceptron learning.
So you see, perceptron cannot separate three classes with just single line.
Hard to separate three classes with just one line.
So what can we do?
Black box approach to multiclass. Abstraction. We have a generic binary classifier. How can we use it to solve our new problem? Can we solve our multiclass problem with this?
Can we solve multiclass with binary classifier? Yes, we can. We will see that. How can we solve it? Approach 1. Okay, this is the first approach to solve multi-class problem with binary classifier. Okay.
Approach 1. 1 versus all over. Training. For each label L, pose as a binary problem. All examples with label L are positive, all other examples are negative.
So what we do is, first we train apple versus rest. Okay, so the apples are +1 and the rest are -1. So at the second time we train as orange versus rest. Orange are 1 and the rest are -1. And at the third stage we train banana versus rest. So banana is 1 and the rest are -1. So this is 1 versus all.
OVA, linear classifiers, e.g. perceptron.
So with linear classifier, with binary classifier, with perceptron, we obtain these three lines which can separate all data correctly. Okay. So this area is pineapple versus rest. This area is apple versus rest, and this area is banana versus rest. So how do we classify? Okay, OVA. 1 versus all classify. How do we do that?
If classifier doesn't provide confidence, this is rare, and there is ambiguity, pick one of the ones in conflict.
Okay, so we have learned our model and a new data came which doesn't fall into any category, and our classifier doesn't have confidence. Then we pick one of them randomly. If not, pick the most confident positive, and if none, vote positive, pick least confident negative. Okay, so there is a decision boundary like this. So how do we calculate this for perceptron algorithm? The prediction is like this: distance from the hyperplane, and the least distance having 1 can be the most confident one. Okay, the other version is all versus all.
Training. For each pair of labels, train a classifier to distinguish between them. For I equals 1 to number of labels, for k equals I plus 1 to number of labels, train a classifier to distinguish between label and label. Create a dataset with all examples with label labeled positive and all examples with label labeled negative. Train classifier on this subset of the data.
Okay, so it can be visualized like this. Apple versus orange will be apple plus 1, apple plus 1, orange will be minus 1. Orange versus banana will be orange plus 1, banana minus 1. And the apple versus banana will be apple 1, banana minus 1. You see, each time we use a binary classifier, therefore we generate 3 different models and we merge them. So when this comes, it will be orange. Okay. How do we decide that? It will be check it versus each of them. So in this case, it will be orange. It will be orange versus banana. Orange will get positive 1. And therefore it will be classified as orange. Okay. Okay, I will just pass this. Okay, how should we wait? Accuracy, data imbalance. Okay, there is confusion matrix. So confusion matrix shows our real class and predicted class. Let's say we have 6 different classes. So the real class is classic and it is predicted as classic 89. Real class is classic and the predicted class is 2. I mean country, so there are 2. You see, it shows real class and the predicted class like this. So this is called as confusion matrix. Okay, so I will look for a better example to illustrate. One versus all binary classifier. So let's find a better example. Okay, I think a good example is multiclass neural network. This time we will use multiclass perceptron. I mean, we will use perceptron network to do multiclass. Okay, so okay, so this is a good example.
One versus all provides a way to leverage binary classification. Given a classification problem with n possible solutions, a one versus all solution consists of n separate binary classifiers, one binary classifier for each possible outcome. During training, the model runs through a sequence of binary classifiers, training each to answer a separate classification question. For example, given a picture of a dog, 5 different recognizers might be trained, 4 seeing the image as a negative example, not a dog, and 1 seeing the image as a positive example, a dog. That is, is this image an apple? No. Is this image a bear? No. Is this image candy? No. Is this image a dog? Yes. Is this image an egg? No.
Okay.
This approach is fairly reasonable when the total number of classes is small, but becomes increasingly inefficient as the number of classes rises. We can create a significantly more efficient one versus all model with a deep neural network in which each output node represents a different class. The following figure suggests this approach.
Okay, so this is the neural network. We have made example of this. There are hidden layers and input. Input layer is composed of as the number of features we have. Then we set inherently, or let's say heuristically, number of hidden layers. Then the output layer will be equal to number of classes we have, and it will tell us which one has the most confidence. Therefore we will pick the most weight having one output as the output class. So this is one versus all as neural network. There are also support vector machines for multiclass classification. We will see that in the following lectures. Let's try to find something better, perhaps. Okay, you see these are hidden network, neural networks, and you get probability of the which one is the output. This is taken from the video which I have given you the link for you to watch. I hope you have watched it. It clearly explains how the system works. Okay, input layer, hidden layer, output layer, which works pretty well. Okay, I will try to find something better. Maybe we can see. Okay, so you see one versus the rest, one versus one, and this is the two methods. Okay, and these are the codes for Python. Okay, I think you get the idea. There is also macro averaging and micro averaging. Let's find a good examples for them. There is also support vector machines, which uses binary classification as well. I think I will show it in the following future lessons. Let me check something. Okay, so it generates hyperplanes to separate each label, each class. Okay, and you see there are also academic articles, support vector machines for multiclass classification, written when? What is the date of this? 99 probably. Okay, there are 2006. Okay, all are academic articles. Okay, Okay, so the support vector machines are very effective in higher dimensional spaces, which means if you have so many features to classify, support vector machines are extremely efficient. Okay, still effective in cases where number of dimensions is greater than number of samples. Use a subset of training points in decision function, called support vectors. Versatile. If the number of features is much greater than the number of samples, avoid overfitting in chosen kernel functions. Okay. And okay. You see, SVH and new SVH implement one versus one approach for multi-classification. In total, n classes plus multiply with n classes minus 1 over 2 classifier are constructed, and each one trains the data from two classes. Okay. To provide a consistent. Okay. So you see, when you do multi-class classification, you actually generate n number of models, or n multiply with n minus 1 over 2 number of classifier models to decide which one is the correct one. So it uses 1 versus 1. So which ones they get most positive gets that label. So this is not efficient. This is not as efficient as neural networks. Therefore, if you have multi-class problem, you should use neural networks instead of SVMs. SVMs are very powerful in less number of classes. Okay, someone had asked that. Okay, so each one has weaknesses and strengths.
Tree methods are good if 1. You have lots of predictor variables and data. 2. Your test set values are within the range of values found within the training set for both predictors and response. Trees tend to suck at extrapolative predictions, although they have some success with panel data. 3. Suitable predictor variables are denoised, e.g., wavelet transformation, etc. SVM are likely better than tree methods if.
Okay, I think this answer is not very good. Anyway, these are all related to your experience. You just need to get idea. However, I can say that if you have lots of classes, use neural networks. If you have fewer classes, if you have lots of classes and not that many input features, use neural. If you have fewer classes and so many features such as text classification, use SVMs, support vector machines, and the others are also up to your problem. I can say at least these two though. Okay, so we are going to see macro averaging and micro averaging.
Micro average versus macro average performance in a multi-class classification setting. Ask question. I am trying out a multi-class classification setting with 3 classes. The class distribution is skewed with most of the data falling in one of the 3 classes. Class labels being 1, 2, 3, with 67.28% of the data falling in class label 1, 11.99% data in class 2, and remaining in class 3. I am training a multi-class classifier on this dataset and I am getting the following performance.
Okay, so you see, when you have unbalanced data, you have to do something. Okay, because you don't have a balanced data. So let's see what is the answer they have given.
285 micro and macro averages for whatever metric will compute slightly different things, and thus their interpretation differs. A macro average will compute the metric independently for each class and then take the average, hence treating all classes equally, whereas a micro average will aggregate the contributions of all classes to compute the average metric. In a multi-class classification setup, micro-average is preferable if you suspect there might be class imbalance, i.e. you may have many more examples of one class than of other classes. To illustrate why, take for example precision PR equals TP, TP plus FP, PR equals TP, TP plus FP. Let's imagine you have a 1 versus all, there's only one correct class output, per example, multi-class classification system with 4 classes and the following numbers when tested.
Okay, so TP is true positive and VP is false positive. So here you are calculating the precision, and therefore if you have unbalanced multi-class problem, they suggest you to use micro average. So the example is like this.
Class A, 1 TP and 1 FP. Class B, 10 TP and 90 FP. Class C, 1 TP and 1 FP. Class D, 1 TP and 1 FP.
So this means that there is the classifier has classified as class A 1 true class A, 1 false class A. So the confusion matrix of this would be like this: A, B, C, D, and A, B, C, D. So 1 positive. Okay, and let's say we can't get confusion matrix from here. So this means that the algorithm has classified class A 1 times correctly and 1 times incorrectly. This means that classifier has classified class B as 10 times correctly and 90 times it was incorrect. And this means that the class C was 1 times correctly and 1 times incorrectly. This is that. You can see easily that. Let's read it.
You can see easily that PRA equals PRC equals PRD equals 0.5, PRA equals PRC equals PRD equals 0.5, whereas PRB equals 0.1.
Okay, so precision is calculated as like this if we accept that. So this is the precision as 0.5, this is 0.1, this is 0.5, and this is 0.5. When you use macro average, the average of all is being 0.4, and if you use micro average, it is being 0.123. This is more correct because in this case we have correctly classified 13 times and incorrectly classified 93 times. Okay. So let's say in machine learning, let's learn the precision as well because it is important. Precision and recall.
Precision and recall. In pattern recognition, information retrieval and classification, machine learning, precision, also called positive predictive value, is the fraction of relevant instances among the retrieved instances, while recall, also known as sensitivity, is the fraction of the total amount of relevant instances that were actually retrieved.
So
both precision and recall are therefore based on an understanding and measure of relevance.
Okay, so in this picture, I think it is well explained. These are the relevant elements and false negatives. Therefore, they have been marked as negative, however they were relevant. Okay, since you have marked as unrelevant the truly relevant elements, they are marked as false positive. Here these are true positive because they were relevant and you have classified them or marked them as relevant. And here true negatives because they were unrelevant and you have classified or predicted them as unrelevant. And these are false positives. Why? Because they were irrelevant, they were not relevant, and you have marked them as relevant. So think about that. This circle is the your uh, predicted labels, and the left side were correctly predicted and the right side was incorrectly predicted. So this is true negative, this is false positive, this is true positive, and this is false negative. Okay.
Suppose a computer program for recognizing dogs in photographs identifies 8 dogs in a picture containing 10 cats and 12 dogs, the relevant elements. Of the 8 identified as dogs, 5 actually are dogs, true positives, while the other 3 are cats, false positives. 7 dogs were missed, false negatives, and 7 cats were correctly excluded, true negatives. The program's precision is 5/8 true positives, all positives, while its recall is 5/12 true positives, relevant elements. When a search engine returns 30 pages, only 20 of which were relevant, while failing to return 40 additional relevant pages, its precision is 20/30 equals 2/3 while its recall is 20/60 equals 1/3. So, in this case, precision is how valid the search results are, and recall is how complete the results are.
Okay, so this is a really good explanation of what is precision and recall. Let's read it again.
Suppose a computer program for recognizing dogs in photographs identifies 8 dogs in a picture containing 10 cats and 12 dogs, the relevant elements. Of the 8 identified as dogs, 5 actually are dogs, true positives, while the other 3 are cats, false positives. 7 dogs were missed, false negatives, and 7 cats were correctly excluded, true negatives. The program's precision is 5/8 true positives, all positives, while its recall is 5/12 true positives, relevant elements. When a search engine returns 30 pages, only 20 of which were relevant, while failing to return 40 additional relevant pages, its precision is 20/30 equals 2/3 while its recall is 20/60 equals 1/3. So, in this case, precision is how valid the search results are, and recall is how complete the results are.
Okay, I think this is a really good explanation. And maybe we can find some more infographic. I will check. Okay, there is also F1 score. It is used like this. Precision recall F1 score is 2 multiply precision multiply recall over precision plus recall. And there is accuracy true positive plus true negative over total. So this is F1 score and this is accuracy and this is precision and recall in this example. Okay. Anyway, you can look for this if you want. There are a lot of resources. However, in academic research, these are given: accuracy, precision, recall, and F1 score. I have also used these in my thesis. Let's find my thesis. I have uploaded it to here. Yeah, and F1 score, if you type, why it can't. Okay, so the precision, I also explain it, page 62. You see, I explain the precision, recall, accuracy, and F measure. These are the 4 used measurements to evaluate results. Okay, and I believe I have given them, okay, here. So you see the f is, let's find, yeah, probably f1 score, precision and recall, yes. Anyway, this is how we compare different algorithms. You see, I have compared different distance metrics with different linkage criteria with DT algorithm, I think decision tree, or distance threshold. And okay, so this is how you compare different algorithms and compare their performance. You see cosine distance, centroid linkage clustering, and such. And f measure, okay, here they are given f measure, area, precision, recall. F1 score is pretty much accepted one, I think. And now we know the macro average and micro average. So let's continue to read this one.
For computational reasons, it may sometimes be more convenient to compute class averages and then macro average them. If class imbalance is known to be an issue, there are several ways around it. One is to report not only the macro average, but also its standard deviation for 3 or more classes. Another is to compute a weighted macro average, in which each class contribution to the average is weighted by the relative number of examples available for it. In the above scenario, we obtain.
Okay, so if we use macro average mean, we get 0.4. If we use macro average with standard deviation, we get 0.173. If we use macro average weighted, you see they are multiplied with their relative number of examples, we get 0.123. So it is equal to micro average. And
The large standard deviation, 0.173, already tells us that the 0.4 average does not stem from a uniform precision among classes, but it might be just easier to compute the weighted macro average, which in essence is another way of computing the micro average.
so therefore you should use micro average. Okay, I think this was a good example. There are also other examples. Okay, so we have seen that. So this is the confusion matrix. We have seen that as well. Okay, now you get the idea. For calculating success of your algorithm, if you are using a multiclass, you should use F1 or F1 score. I think it is the best one, I believe. And you should also calculate accuracy, precision, recall. However, the F1 score is the perhaps best one. You can also look for some explanation related to that. You see, data science of stock exchange is really good for such questions. Balanced accuracy versus F1 score.
I've read plenty of online posts with clear explanations about the difference between accuracy and F1 score in a binary classification context. However, when I came across the concept of balanced accuracy, explained e.g. in the following image source or in this scikit-learn page, I was a bit puzzled as I was trying to compare it with F1 score.
So you see, regular overall accuracy is a lot different than balanced accuracy. Oh, not much different. Okay, so someone has made an answer.
One major difference is that the F1 score does not care at all about how many negative examples you classified or how many negative examples are in the dataset at all. Instead, the balanced accuracy metric gives half its weight to how many positives you labeled correctly and how many negatives you labeled correctly. when working on problems with heavily imbalanced datasets and you care more about detecting positives than detecting negatives, outlier detection, anomaly detection, then you would prefer the F1 score more. Let's say, for example, you have a validation set that contains 1000 negative samples and 10 positive samples. If a model predicts there are 15 positive examples, 5 truly positive and 10 it incorrectly labeled, and predicts the rest as negative, thus.
So it is being like this. So the F1 score precision will be 0.33, recall will be 0.5, F1 will be 0.4, and the balanced accuracy will be 0.745.
You can see that balanced accuracy still cares about the negative data points, unlike the F1 score. For even more analysis, we can see what the change is when the model gets exactly one extra positive example correctly and one negative sample incorrectly.
Okay.
Correctly classifying an extra positive example increased the F1 score a bit more than the balanced accuracy. Finally, let's look at what happens when a model predicts there are still 15 positive examples, 5 truly positive and 10 incorrectly labeled. However, this time the dataset is balanced and there are exactly 10 positive and 10 negative examples. You can see that the F1 score did not change at all compared to the first example, while the balanced accuracy took a massive hit, decreased by 50%. This shows how F1 score only cares about the points the model said are positive, and the points that actually are positive, and doesn't care at all about the plethora points that are negative.
Okay. So, in which scenario, for example, you would have such dataset? For example, let's say you want to mark spam mails and you get 1000 mail that is not spam and you get only 2000 mail that are spam. So your aim would be detecting that two spam mail out of 1002 mails. If you mark all of them as correct mail, as let's say non-spam mail, you may get very high accuracy. However, it would be pretty bad prediction because we want to only detect spam mails and mark them as spam. Also, based on your problem, you need to pick the correct algorithm and let's say metric for evaluation. Okay, like here, predicted classified negative 1998 and one positive and one positive like this. Therefore, in such cases, accuracy is not the way we go. So I think F1 score is being the best one in such cases. Yes. And
Accuracy is used when the true positives and true negatives are more important, while F1 score is used when the false negatives and false positives are crucial. Accuracy can be used when the class distribution is similar, while F1 score is a better metric when there are imbalanced classes, as in the above case.
so if your data is unbalanced in terms of classes, such as in classifying spam. Okay, let's think that you want to classify emails as non-spam and spam, and you will have like 1000 non-spam mail and 2 spam mails. In this case, you cannot use accuracy. Why? Because if you classify all mails as non-spam, you would get accuracy of 1000 over 1002. You see, it is more than 99% accuracy. However, in reality, we have misclassified our aim, our target, which was spam mails. So actually, we have 100% failed. Therefore, in this case, we need to use F1 score. So let's calculate F1 score of such classification. So let's check the algorithm. The algorithm is like this. First, we calculate the accuracy. Then, first we need to calculate precision and recall. So the precision is true positive over true positive plus false positive. So how many true positive we have? I am considering true positive as spam mail. We have 0 true positive. And how many true positive plus false positive? We have like this. So we get 0 point from precision. We have 0 precision. And how much recall we have? True positive over true positive plus false negative. How many true positive we have? We have 0 true positive. So we get 0 recall as well. Therefore, our F1 score would be 0. Okay. So that is the difference. So let's add some numbers to evaluate it better. Let's say we have 1000 non-spam and 1 spam and 3 spam but marked as non-spam. Therefore, our accuracy would be 1 over or 1000, yes, 1000 over 1000 for accuracy, and F1 score would be, so the precision is in this case true positive 1 over true positive plus false positive. How many true positive we have? 1. And how many false positive we have? 1000. So the precision is 1 over 1003. Recall would be how many true positive we have? 1. How many true positive plus false positive? 1 plus false negatives. False negative we have 3. So the recall would be 1 over 4. And how many, what would be our F1? It would be 2 multiply with precision multiply with recall. So precision is 1 over 1003 multiply with 1 over 4. And it will be a bit over precision plus recall like this. 1 plus 1 over 4. Okay. So you see F1 score is being really low. Like, let's add some parentheses to calculate them in calculator. Okay. Okay. And let's copy paste this to calculator. So we get F1 score of 0.25 in this case, and we get accuracy of 1000 over 4 as, sorry, let's delete this, over 1004. We get 99.60 accuracy, however we get only 0.25 F1 score. Okay, so you get the idea of F1 score importance. If you have any questions, please ask me from my email or from our Discord channel. Okay, there is one more thing. We are going to make an additional rule to your project from, let me copy paste it from this one. This rule is actually nothing new, I mean nothing extra work for you, but it is an additional thing to correctly evaluate your lecture attendance. Here. So what you need to do is, as extra, okay, let me paste it. Everyone will be sending a Word or PDF document along with their final project files. This document will contain screenshots of your all comments to the lecture videos, all of the 14 lecture videos or more if we have, or more if we make. You will take screenshots in high resolution. Your comment has to be clearly readable. Those who fail to send this document will be counted as not attending to lectures, therefore they will get FF. So this is really important. Along with your video, you will send your screenshot document as well. Let me update this, and this will be also updated on GitHub version 2. Okay, I'm going to save this. Also, please try to avoid from coronavirus. It is a really dangerous disease. Don't take it lightly. You may get cured with easiness. However, your relatives or your friends may not be that much lucky. I have lost my grandfather from coronavirus recently, so please be careful. Okay, and one more document I will update. Okay, let's remove this, and okay, let's push the lecture slide. Oh, not this one. Okay. Lecture 9 slides and final project description update. Okay, we are updating our GitHub repository. We are looking for volunteers to our subtitle project. Please also consider helping that. Okay, end of lecture. Hopefully see you next week.